So I think the best place to go next with this is see what we could do with exponential functions. Now that we have 2 to the power of n, I would like to be able to say something about 3 to the power of n or some arbitrary powers of n. So I want to kind of come up with a cookbook way of dealing with this. So I go from like 2 to the power of n to say 5 to the power of n, or some arbitrary L to the power of n to U power of n. So that's going to be the next thing we're going to do here. So let's take a look at this. So you're going to see that the bits and pieces that make this claim work for our first basic example are actually going to be very easy to generalize. So I want you to take note of the fact that sometimes things only being 2 or 3 or 4 may not actually matter. The technique might actually be a little bit more general than just that. So we're going to try proving that 2 to the power of n is big O of 3 to the power of n. So as per usual, we need to lay out our game plan for how we would do this. So we find constants. We find constants. We find constants C and n0, which is a positive integer, right? Such that for all n greater or equal to n0, I had to kind of squish it in there. For all n greater or equal to n0, 2 to the power of n is less than or equal to c times 3 to the power of n. So we've seen when we deal with exponentials that we can actually apply logarithms to both sides of these inequalities. Well, let's try doing that here. Now I have a 2 here and I have a 3 here, and I know that exponential functions like these are increasing functions. So if I have a 2 here and I have a 3 here, notice that 2 raised to something, at least the intuition behind this should be, it should be less than the 3 to the something, because every time I increase n, it always makes this side, while it goes up, it doesn't go as fast up as the 3 to the power of n. So we're going to pick c is equal to 1. Then what we're going to do is we're going to take logarithms to both sides of the inequality. So now what we have to do is find the n0. We find n0 where log base 2 of 2 to the power of n is less than or equal to log base 2 of 1 times 3 to the power of n, which this has to be for all n greater or equal to n0, right? Well, here's the thing. Remember the power rule of logarithms? So remember, I could pull this n out front. Notice that this one, it's 1 times that, so I could just rewrite this as this. So this is just n times log base 2 of 2. And this is just n times log base 2 of 3. But here's the thing. What's log base 2 of 2? That's equal to 1, right? But what's this? This is because log is an increasing function. So log base 2 of 3 has to be greater than 1. So it's greater than 1. So I have n is less than or equal to n times something slightly bigger than 1. So that most certainly doesn't make it smaller, it gets bigger, right? So that means that we can use this fact right away. So notice that log base 2 of 2 is equal to 1, which is less than log base 2 of 3. And this is because logarithm is an increasing function. So for all n greater or equal to 1, n times log base 2 of 2 is equal to n, which is less than or equal to n times log base 2 of 3. So we're just going to simply choose n0 is equal to 1, and then we're done, right? Well, we're not quite done, right? We still have to invoke the definition of big O. Because now we have the two constants I can present to somebody. So let's do that. So therefore, by the definition of big O, to the power of n is big O of 3 to the power of n. Okay, so now we know that 2 to the power of n is big O of 3 to the power of n. Wonderful, right? Now you might be staring at this and saying, Dan, there's a lot of stuff here akin to some of the previous things we've talked about, like the idea of how we could generalize our ideas. Can we generalize this claim even further so we can say more about exponential functions? So what I want to do is I'm going to presume that we have two positive reals, L and U. Let positive reals L and U exist so that, oh yeah, they also have to be greater than 1. That's another catch with this. Because remember, if we're trying to apply logarithms, we want to be very careful. We want to make sure that we're just going to be careful here. Now, there's more things you could say potentially, but this is what I'm going to restrict things to. I think this is a pretty nice basic generalization. So L and U are greater than 1, where L is less than or equal to U. So what I want to do is I want to take this, and we're going to try generalizing this proof so that it's not just 2, it's L. L to the n is big O of U to the n. So I would like to generalize our ideas here. So let's walk through what we have here on the board, and let's see if we can generalize our ideas. So we have the two constants, right? That's all okay. So I'm just going to replace the 2 and the 3 with L and U. So far, the reasoning seems pretty clear so far. We haven't deviated from the claim up above. And what we're going to do is we're going to still pick C is equal to 1, because remember, L is less than or equal to U. And if we keep the intuition we had last time about 2 versus 3, it should extend for anything that is 1 where L is less than or equal to U, right? Because of the nature of exponentiation being increasing functions, but also logarithms being increasing functions too, right? At least the way that they're going to manifest themselves in the way we play around with this. So pick C is equal to 1, then we take logarithms on both sides, so we find n0 such that where L to the n is less than or equal to 1 times U to the n. If we play around with this, we end up with log base something. Now, I'm going to set the base to be L. Why? Because then I have log base, so I have n times log base L of L, which will equal, what does that equal? It equals 1, right? So I'm trying to come up with a way to kind of generalize this. So if I take base this, I have to take the same bases to both sides because of the way we're playing around with this. I already had some discussion about this earlier, right? So I have this, and we know, so we can notice the following. We could say log base 2, sorry, log base n, sorry, log base, not L, not n, sorry, not 2, not n, but L of L is equal to 1, but this has to be less than log base L of U. This is because L is less than or equal to U, right? So, for all n greater or equal to 1, n times log base L of L is equal to n, because it's just 1, right? And then we have that's less than or equal to n times log base L of U, which this has to be strictly greater than 1, right? If L is in fact less than U, but if they're equal, this should be an equality, not an inequality necessarily. So we get this for all n is greater or equal to 1. Oh, yeah. So we got this. That's wonderful. And that looks like we're in pretty hunky-dory mode, right? So we can choose n0 is equal to 1. Then we can say, therefore, by the definition of big O, L to the n is big O of u to the n. And we're done. I forgot my fun box to finish off the proof. So notice that now we have a much more general proof that tells us relationships between different exponents.